and welcome back to Atman Unlimited. Let's talk about thread milling. Thread milling is another type of threading operation that you can do on your CNC machine to generate threads in a part. Unlike rigid tapping that we covered before, thread milling can be done on pretty much any machine that has full 3-axis control. The reason you need a full 3-axis machine is we have to synchronize XY circular interpolation with a Z feed to generate a helical pattern. In thread milling, what we do is we take a cutter that has the profile of the thread we want to generate, and what we'll do is we'll circular interpolate the cutter in XY while we feed in Z. So we'll make the helical pattern of the thread that we want to use. That's why you must have a 3-axis machine to do it. Here is what a standard thread mill looks like. This is a single point UN thread mill. If you notice, it's basically just cut in the profile of a standard thread. This is a single point cutter. It will cut one thread per pass, so you have to do multiple circles all the way up your part in order to generate a complete thread in your part. They also make thread mills that are multi-point so that you don't have to do a full revolution for every single thread. They come in a variety of depths and lengths so that you can do multiple threads with only one complete circular pattern. Now that we have a good definition of what thread milling is, let's talk about the advantages of thread milling. Like we said previously, pretty much any 3-axis machine can perform thread milling. Unlike rigid tapping that requires a special 4th-axis controller around our spindle, the thread milling operation can be done as long as you have the accuracy in a 3-axis machine. Unlike with tapping, if you break a tap off in your part, the tap is not going to be easy to extract once it's broken. Most people will use an EDM machine to burn the tap out of the part. Most hobbyists or garage shops don't have an EDM machine readily available. With a thread mill, typically the thread mill is smaller in diameter than the hole. Therefore, if it breaks, it's just going to fall out and we don't have to scrap our part. We can put another thread mill in and we should be able to finish the threads up with the new thread mill. Thread milling also generates a cleaner, stronger thread than you would typically get with tapping. If you're trying to generate threads in very hard materials like titanium, Inconel, Hastelloy, any of the exotic materials, thread milling is definitely the way to go because it greatly reduces the cutting forces and it generates a much cleaner thread. The last advantage to thread milling is we can generate a large range of thread sizes, and if you're using single point threads, thread pitches, using only one tool. So if you're using a single point thread mill, that single point thread mill will be able to generate a wide range of pitches and a wide range of internal and external thread diameters. So with one single tool in our machine, we can generate a lot of threads. If you're using a multi-point threading tool, it will be limited to the size of, or to the pitch that it's specified for. However, it will still be able to do multiple sizes, both internal and external, as long as that thread mill will be able to fit inside your hole on your internal threads. One of the disadvantages to thread milling is it's going to extend your machining time. Typically, you'll be able to do a tapping operation much faster than you'll be able to do a thread mill operation, especially if you're using a single point thread mill, because a single point thread mill will require you to mill the entire circle of the thread for every single thread that you need to generate. So thread milling with a single point thread mill can take considerably longer than if you were to use a tap. One of the biggest stumbling blocks to being able to thread mill effectively and repeatedly is generating the CAM code and the G code to do your threads. With Fusion 360, there is a thread milling operation inside Fusion 360, but I have not been able to find any good resources that describes how you should set the starting material diameter of your part and also what you should set the diameter offset for the thread mill operation. This can be a little bit muddy, and it's going to take a little bit of understanding of thread dimensioning and thread tolerancing. So we're going to have to go a little bit in depth in how a thread is dimensioned and how a thread is toleranced so that we understand how to generate the numbers that we need to enter into Fusion 360. Unfortunately, I see a lot of people guessing at these numbers, and it will work. You may have to run a couple of test parts and test fit them together. You'll get there. But if you have a better understanding of what those numbers mean and how to come up with those numbers repeatedly and accurately, it will make your thread milling experience much more enjoyable. Let's head into the office and we'll pull up some diagrams of some threads, and we'll go over how a thread is first toleranced and what the tolerances around a thread are, and how those tolerances play into the dimensions that you give Fusion 360 to be able to successfully generate your thread the first time, every time. We're back in the office. Let's take a look at a cross-sectional diagram of a thread and see how we dimension and tolerance threads so that we know how to configure Fusion 360 for our thread milling operation. So here we have a cross-sectional view of a standard thread. This is courtesy of Wikipedia. I'll include the Wikipedia page in the video description. There's a lot of things here that describe the geometry of the thread, but for thread milling, we're really only interested in these diameters over here and these couple of H values over here that describe how to get to the different diameters of the thread. The rest of the geometry is taken into account by the thread mill when they manufacture the thread mill. So the diameters are what really we're interested in, and every thread has 3 diameters associated with it. A major diameter, which is the largest diameter in the thread. If it's an external thread or a bolt, that will be the diameter that you measure with a pair of calipers on the bolt itself. You have a minor diameter, which is the smallest diameter in the thread. That would be the root of the threads on a bolt, or that's the smallest, that's the inside diameter of a nut. And then we have what's called a pitch diameter. Now the pitch diameter is an imaginary line that's drawn through the center of the teeth of the thread. So if you picture the thread as a triangle, so here's the peak of a triangle, there's the other peak of a triangle, this pitch diameter goes right through the center. Now a lot of people think that the thread fit is by the major or minors, but that's not the case. The pitch diameter is what drives the fit of a thread. So this pitch diameter in this diagram is drawn ideally with both the internal and external threads having the exact same pitch diameter. In reality, what we do is we offset this pitch diameter so that the internal thread or the nut is a little bit bigger pitch diameter, and the external thread or the bolt is a little bit smaller pitch diameter, and that will pull these two triangles apart a little bit so that there's a little tiny bit of clearance between the two of them. That's called thread allowance, and that's applied to class 1 and class 2 threads. If we didn't have that allowance, or if we machine these threads a little bit too tight and these pitch diameters crossed, now you would be into an interference fit and your parts wouldn't screw together. So the pitch diameter is what really drives the fit of a thread. It's also one of the most critical dimensions on a thread, and it's often overlooked when making threads either single point threading or on a lathe. The major diameter and minor diameter are important, and they do have tolerances associated with them. But if we machine these larger or smaller, as long as we don't pass the triangles of the thread will still screw together the same way and have the same fit. What the major and minor diameter dimensions do is it controls the area of the thread, and then that will control the strength of the thread. So the less area we have in the thread, the less strength you may have in the thread. When you're selecting your drill size for a tap, what you're doing is you are controlling this minor diameter. If we're using soft materials, you might do a little larger minor diameter. If you're doing some very hard materials, you're going to select a larger drill and you're going to drive this minor diameter a little smaller. So that's what you're doing when you're selecting your drill sizes for a tapped hole. So how does this all relate to Fusion 360, and how can we thread mill our threads? So let's go over to Fusion 360 real quick. So I have Fusion 360 open, and I've got two models already made. This one is just a cylinder. It's going to be our external thread. This one is a cylinder with a bore in it, and this will be our internal thread. So the first thing that we need to figure out is how big do I make my cylinder, or how big do I make my bore, so that I have the correct starting diameters before I even start thread milling. And those are pretty easy to calculate. So if we go back to our diagram, what we want to do is we want to calculate this major diameter, and on a standard thread that's pretty close to the nominal. So in our example we're going to use a 1.25 inch thread, so this diameter is going to be close to 1.25 inches. The nut takes a little bit, or the internal thread of the nut takes a little bit more math to figure out, because normally you've got to start with your nominal diameter, and then we have to figure out, using these formulas over here, how to calculate this down here. So where do I come up with these numbers? So H is simply a calculated number based on the pitch. So in the English threads we specify threads in how many threads per inch. The pitch of a thread is the reciprocal of that. So in this case we have a 20 threads per inch example. 1 over 20 is 50 thousandths, 0.05. So that's what P is. To calculate H, we just take the cosine of 30 and multiply it times P, and that gives us this H value. So let me pull up all the calculations that we're going to eventually need. So that's this calculation here. So H equals 1 over the thread pitch, the threads per inch, times the cosine of 30, and that will yield H. Okay, so anywhere you see an H, that's what that number is. Now for an external diameter thread, to calculate the external diameter, what we need is we need the nominal thread diameter, 1.25 inches, and then we have to subtract off a tolerance and a thread allowance. So where do we get these tolerances from? Well, a lot of people still do and used to use a machinist handbook. However, a lot of people have made nice calculators online. This is one of my favorite thread calculators. It's done by the theoretical machinist. Now he's got a whole bunch of list of standard and non-standard threads that you can select from here. And if you don't find a thread in the list, you can just simply type in what you want your nominal diameter to be, how many threads per inch you want, and your fit, and hit compute, and then it will give you all the values that you need. So for our example, we're going to do a 1.25 inch thread by 20 threads per inch. Once we have that decided, then we have to figure out what kind of class thread we want. So the class of a thread is how they define the tolerancing of a thread, and it goes from 1 to 3. A class 1 thread has the widest tolerance, and it's the loosest fitting thread. A class 3 thread has the tightest tolerance, and it's the tightest fitting thread. Class 3 threads are typically seen in aerospace and military, but not much more than that. Anything that you have a really high accuracy problem to solve, that's typically when you'll see a class 3 thread. Class 2 threads are the most common, and the reason for that is it's a nice balance between a class 1 thread of being easy to make, but yet still being tight enough like a class 3 thread so that we get the strength of the thread. So class 2 is a nice balance between ease of machining versus the strength of the thread. Now you notice in addition to the class number there's also a letter. It's A or B. That simply just designates whether it's an external thread, an A, or an internal thread, a nut, B. So for this we're going to look at the external thread first. We'll select 2A and hit compute. And then these are all your diameters that we were just talking about. And then here's all your tolerances. So if we switch back to our diagram, we've got a major, a pitch, and a minor. So here's your major window. So this is the high side, that's the low side. You have to be within these two numbers. There's your pitch diameter, and there's your minor diameter. The way that these are calculated is we take the nominal thread, for an external thread, we would subtract off the allowance, and then we would subtract off also the tolerance. So with the nominal minus the allowance, that should give you this number here, and then that is the target perfect thread dimension to meet. Now they give you a tolerance because they know in the real world we need some leeway in our manufacturing. So that's where this major diameter tolerance comes from. And you could be anywhere in here and still be in spec for a class 2 thread. Now if I switch this to class 3, notice two things happen. One, the allowance goes away, so there's no more allowance. What that means is with a class 3 thread, if you're at the very absolute top of the external thread and the very absolute bottom of the tolerance on an internal thread, then your thread is going to have zero clearance at all. It's going to be a very tight thread. That's why class 3 threads are harder to machine, because you have to hold your tolerances very tight. Also notice your pitch diameter tolerance dropped down to 3.5 thou. Now that's not plus or minus, that's total. So on a class 3 thread of this size, you need to hold the pitch diameter within 3.5 thousandths total. Class 2, they give you a little bit more leeway. You got 4.7 thou. Class 1, they give you a lot of leeway. You've got 7 thousandths. So you can see as the class changes, the pitch diameter tolerance changes quite a bit. Now one thing also to notice, if we go to a class 3A, the major diameter is 8.1 thou, but on a class 2A, it's still 8.1 thou. And again, the reason for that is the pitch diameter is the most critical dimension of a thread. The major and minor diameters control the area. So then let's go back to our calculations and figure all this math out. So if I want to figure out how big to make the external diameter of my stock in Fusion 360 before I start thread milling, I'm going to take my nominal diameter, 1.25. I'm going to take the major diameter tolerance from my thread calculator from Practical Machinist. I'm going to put a tolerance factor on that. Now what I do is I have this tolerance factor that goes from 0 to 1, and it's just a percentage. Typically I shoot for 50%. That gives me a little bit of leeway on each side of my tolerance for my machining, and I typically never have a thread that's out of tolerance. If I'm machining something that I know I want a little tighter, I'll lower my tolerance factor down and it will automatically machine a little tighter for me. If I want something to be a little bit looser, I'll increase the tolerance factor and I'll be a little looser. Now, if I'm not at 50% of my tolerance factor, I know I'm taking some of my tolerance off either way, and I might have a harder time hitting the thread in spec, based on how close I am to the limits. So that's what the tolerance factor is, and typically I set it to 50%. So major diameter tolerance times my factor, and then you add in the thread allowance, that all gets subtracted off of the thread diameter. Now I also made a little calculator for myself. In some of my other videos I mentioned that I do LabVIEW code, so I wrote a little LabVIEW calculator. You can just as easily take these numbers, calculations, and put them in Excel for yourself and have a nice little Excel sheet. So if I take the nominal diameter, my tolerance factor, my major diameter tolerance, and my thread allowance, and crunch those through my equation, I get 1.2446. So going back to Fusion 360, if I measure this part, I want it to be 1.2446. So that's the number I've got it set at. Now for the internal thread, it's again very similar. So if we skip down to the internal thread, I take my nominal thread diameter, and then I need to subtract off h times 0.625, and that's 5/8. And what that comes from, if we look back at our diagram, this is my nominal thread size right here. I need to calculate this value here, which is going to be the internal diameter of the thread. If you look here, we've got 5/8, h times 5/8. 5/8, or 5 times h divided by 8 is h times 5/8. So 0.625. So that's where that number comes from. Now the reason why it's times 2 is because in this diagram, these are radiuses. We need to talk in diameters, so that's where the times 2 comes from. Then I take the same tolerance factor concept and I add it to my minor diameter. So then this will give me the internal diameter to make in my model. So if we go back to my calculator here, I've got a minor diameter tolerance of 11.5 thou. I'm going to apply a half of that to my diameter, and I get 1.2016 inches. So that is what I'm going to want to machine that inside diameter to, if we got 1.2016. So that sets up your stock and your model. Now we actually have to go into the thread milling operations and figure out what to type in for my thread mill setups. Now I already cammed out all the operations to get the stock to this point that you see in the model. We'll walk through the thread milling operations in this video. These are just basic operations just to get it down to this point. One thing I will add is the chamfer. You want to add a nice chamfer anytime you have a thread lead in, whether it's internal or external. And the depth of that chamfer wants to be as deep as the thread, if not a little bit more, so that you get a nice clean lead in and your parts will screw together real nice. So let's look at the numbers that we need to calculate for our thread milling. Now there's two different ways that you can calculate these numbers, and it stems to how you define your tool. So a lot of people will define the diameter of their thread mill tool based on its pitch diameter. If you're doing a lot of single point threading, however, the pitch diameter of a single point thread will be related to the pitch of the thread that you're machining at that instance. So you may have to redefine your tool diameter a bunch of different times because a 16 threads per inch pitch diameter is going to be different than a 20 or 32 threads per inch pitch diameter. And the reason for that is, again, if we take this major diameter of our thread and we want the pitch diameter, it's 3/8 of h, and h relates to pitch diameter. So that's why that changes. If you're using multi-cutter, multi-point thread mills, those pitch diameters are going to be set in stone because that's the pitch diameter of that thread mill. So it's not an issue using pitch diameter with multi-point thread mills. The other method that you can do, and this is the way that I do it, it's independent of pitch diameter. What I do is I calculate the value of this point right here or right here. And then I'll take my thread mill and I'll calculate out in the thread mill what the theoretical diameter is if it came to a sharp point. What that does is that eliminates the dependency on the pitch diameter or the pitch of the thread that we're cutting. So if I'm cutting a 16 thread per inch pitch or a 32 threads per inch pitch, then that tool diameter will be identical no matter what the pitch is. So that's why I use this methodology. Again, it's what you want to use and what fits your circumstance the best. Now the way you get the pitch diameter or this point diameter from your thread mill is a lot of the big shops will have optical comparators, and they'll just take the thread mill over to the optical comparator and measure it. We find that once you decide a manufacturer and you order a whole bunch of thread mills of the same manufacturer and the same part, they're very consistent from lot to lot. So typically you just have to do this anytime you change manufacturers or you get a new thread mill in-house. In a small shop, you're probably not going to have an optical comparator. So a lot of the times what you'll do is you'll have to make some test parts and figure out where those two diameters are depending on the method you're going to use. So let's take a look at the math that we're going to calculate for either one of these, because we want to either calculate, this point here or this diameter here. Now it's not quite as easy as just taking 1.25 and multiplying it by h times 3/8. I wish it was, but it's not. And the reason why is our tolerancing. We have to account for the tolerances that we're applying to the parts, and it's the way that Fusion 360 anchors the depth of how far the thread mill goes into the part. So let's go back to our calculations. For an external, to calculate the external pitch diameter, what we're going to do is we're going to again take our nominal diameter and we are going to apply h times 0.375, again that relates back to our diagram, times 2, which is turning it from radius to diameters, plus our thread allowance. Now remember, external threads, we have to apply the thread allowance, but only for external threads. Then we're going to again subtract off our diameter tolerance, or how much diameter tolerance we want to give ourselves. And then that will give us our pitch diameter. So what a lot of guys do, and this is a little bit of a mistake, is they'll calculate out this pitch diameter, and then that is what they'll type into Fusion 360. And the problem with that is Fusion 360 is basing the pitch diameter offset off of what you modeled the part to be. So you have to subtract these two to get the correct pitch offset. So if you're going to use the pitch diameter method and you're going to have your tool described as the diameter of the tool being the pitch diameter, this is the equation that you want to follow. And it's basically simply just external diameter minus the external pitch diameter. Again, all your tolerancing is accounted for in these calculations, so we can just do a simple subtraction here. If you're going to use the point method of having the diameter of the tool specified by the very point of the thread mill, then this is the equation you have to do. And it's almost identical to the other one, but what we're going to do is we're going to subtract off a little bit more, and that's basically we're going to take off a half of h times 2. And then that will give us our point offset. So let's look at my little calculator here again. So we typed in all of our tolerances from our thread calculator, and here's our pitch diameter tolerance. We're going to use half of it for this example, and then we're going to spit out those two numbers, which are these two, of if you're using the point method, this will be your diameter offset number. If you're using the pitch diameter method, this will be your diameter offset number. So let's apply this and set up a toolpath in Fusion 360. So first I need to define a mill, and for thread milling, Fusion 360 currently does not have a thread mill mill type. So they just have you use a flat mill. And then we have to describe the diameter of the flat mill. Now I'm using the point diameter. So this thread mill is actually a little tiny bit smaller in diameter because the thread mills have radius points on them. They don't have a very sharp point. There's a little bit radius associated with them. But that is the diameter if it came to a sharp point. My flute length is simply just the height of the cutter, and that's about it. That's all you really need to specify for the tool. So to make the thread mill toolpath, we select our setup, we go to 2D thread, select our tool, which is going to be the thread mill. Our feeds and speeds I already set up. Those can come from the manufacturer. Now you just have to select the circular face you want to thread mill. So we'll select our external thread mill face. Now the heights tab, because I'm going to machine this out of a piece of bar stock, what I'm going to do is I'm going to keep the thread mill from hitting the bottom of the stock. So I'm going to offset it 50 thou up from the bottom. And then I like to give myself a little bit at the top too. So I normally give myself a little tiny bit of lead in, not that tiny, a little tiny bit of lead in so the thread mill has a little bit better start. Then we'll go to passes. Now this is where we've got to type these numbers in. So our thread pitch, again, that's just a reciprocal of your threads per inch. So in this case, it's going to be 50 thousandths, which is 1/20. And then this is where this pitch diameter offset comes from. Now remember, this pitch diameter offset is based on the diameter of the face that you selected. So that's why in our math here, it's based on this external diameter. So going back to our calculator that performs this math for us, we're going to type in 0.0741. Come here, type in 0.0741. So that's our pitch diameter offset. Come on. So that's our pitch diameter offset. Now, if you read the sheets from the manufacturers, typically they want you to do not multiple threads, they want you to do multiple passes. And you almost always want to do at least 2 passes. Now the depth of the pass is not going to be a 50% step. You don't want to do that. What you want to do is you want to take a big chunk first, because the first pass you do, you're just going to have a small tip of the triangle cutting into the part, and then the second pass you do, you have a much larger piece of the triangle cutting into the part as you feed it in deeper. So typically you want 65% of your depth on the first pass, 35% of your depth on the second pass, so that's about 12 thousandths of an inch step over that we're going to use. Now keep in mind that the step over is in radius and the pitch diameter is in diameter, so don't take half of this value. It's about a quarter of that value for your step over for the 35% roughly. Okay. Now the other thing that I do is in the linking, I tell it to use helical leads. And what that does is in your lead-in, if you look at this lead-in real closely, let's make this lead-in a little bit bigger. And I typically don't do a linear or vertical lead-in. Okay. If you have the use helical leads in, what it's going to do is it's going to ramp this lead at the same pitch as the thread is at. So if we uncheck this, see how this lead-in flattened out? And when we check it, see how it follows the pitch of the thread? We want to use that so that our lead-in on our thread is really nice. So we always want to select that. So now that is how we configure our external thread. So our toolpath is all set for our external thread. And because we used our calculations and we know what our tolerances are, we know our thread mill, we'll be able to get an accurate repeatable thread the first time. We don't have to guess at it anymore. So let's talk about the internal thread. So the internal thread is pretty much done almost identically as the external thread is. So if we're going to use the pitch diameter tool offset method, again it's just going to be the internal pitch diameter minus the internal diameter, and that will give you your offset. If you're going to use your point method, again it's almost identical, where we've got our internal pitch diameter times our half of h times 2, and then that gets subtracted by the internal diameter. So if we go back to our calculator, we've got our tolerance for our minor diameter and our pitch diameter, and we'll run this, and that gives us a point offset of 0.0623 or a pitch diameter offset of 0.019. So because I'm using our point method, we'll cam this part next. So we'll select our internal thread part, we'll do thread, select our tool, select our face, go to our heights, and again we want to hold off a little bit off the bottom so we don't smash the tool into the bottom, and give ourselves a little bit above the part. Our thread pitch is going to be 0.5 because we're using the same pitch. We'll go back to our calculator and then grab our pitch diameter offset, type that in. We want to do multiple passes. We'll do 12 thou again. We'll go to our linking. We'll use our helical lead, make a little bit bigger lead. And there's our pitch diameter, or our thread milling toolpath for our internal thread. So you can see, by having an understanding of the thread geometry and how the thread geometry relates to these diameters, by understanding your tolerances and how your tolerances are applied to these thread geometries, and then having these calculations to be able to calculate all of this, and understanding what the reference point is on your tool when you're using these calculations, now we take the guesswork out of thread milling and we can produce repeatable and accurate threads without having to make test parts. So let's generate this, this code and send it to the post processor and send it out to the machine, and let's make some example parts. back from the machine. We have our parts made. I actually made 3 sets of these. The ones with C's, those ones are pretty much in the middle of the spec, and then I made a set at the very edge of the spec. This one is right at the very edge of the spec, and then I made a set that are right at the very edge of the low spec. Now with aluminum, you want to try to avoid using aluminum for both sides of your thread whenever possible, and the reasons for that is aluminum gulls real bad. So that thread ran beautifully, and it was there was almost zero play in that thread at all because the tolerancing on it was so tight, and it was so good that after the second time I threaded it together and took it apart, it will never come apart again. So you can see by the testament of pipe wrench jaw marks on it, I've tried my darndest to get this apart, and this will never come apart. So with aluminum, you want to make sure you leave yourself a little bit more clearance in the threads, and then always lubricate them as well, because it will help you with the galling issue. And aluminum is always at risk of galling, so you have to be careful. So let's just compare these real quick. So these 2 threads are at the top of their tolerance. You can see they screw together real easy, and there's a little bit of play there. It's not bad, but there's definitely a little bit of play there. So that's at the very top of a class 2 thread tolerance. So now these ones have hit the thread tolerance in the center. So you can see they thread together just as easy, but you can notice there's a lot less play in them. So just in the tolerancing of a class 2 thread, you can see the difference. So there's one that's in the center of the tolerance, and there's one that's at the plus edge of the tolerance. So, and then this one, hey, there's no play in this one. It's seized up real bad, but this one had virtually no play in it at all at the very, very bottom end of the tolerance. So you can see it's in the middle, and that's as loose as it will get. You can see there's quite a bit of tolerance they give you, but again, in reality, it's not much. It's only you know, about 5 thou total. So the next question you get a lot is, how do you verify your threads? So if you had to make this part for a customer and you did not have the mating part to it, how can you verify this thread so that when you ship it to your customer, you'll know that it will mate to their part? And a lot of people will say, oh, well, you know, optical comparator or some expensive go, no-go gauges. But for an external thread, there's a very easy, cheap way to measure this thread very accurately. And it's called overwires. So here's a piece of wire. And the concept is pretty simple. You have a triangle here. You have a circle here. If we use some basic geometry, we can make the thread pitch diameter, which is the diameter we want to measure, larger than the major diameter by using the circle, and then we can measure that. So let's wrap our wire around it. I'll try to do this on camera. This is where the evolution of the third hand is a bit slow and lacking. So I just wrap this around. Okay. We got it nice and in our threads. And now if you notice, the wire is sticking out a little bit larger than the major diameter. So now we can take our nice high quality Harbor Freight calipers. I'm just using the stuff that most people have in their shop. And then we can measure it, and we get 1.2725. Okay? Now, what do you compare that with? Remember our Practical Machinist website that I like so much? The reason why I like it so much is that it has this nice little over wire section. And this wire is 34 thousandths diameter, so I typed in 34,000 and I hit compute wires. And then you can see that a thread pitch diameter over wires of 2.2725 is pretty much directly in the center of our spec. So we hit this one almost dead on. So that was a good part. So you can see, you can easily tell the external thread pitch by using over wires. We can easily measure the external major thread diameter. You know, that's just this measurement here. We went for 1.2446, I believe. So we're right on that. And we can easily measure the minor inside here. I'm catching the inside lip here. I think we're at 1.2016. So there you go. We nailed that. Now the pitch diameter of an ID thread, if it's a really large thread, you could still use the over wires concept. The website doesn't support doing an internal thread that way, and it's really tricky to try to do that way. But what you can do, because we can accurately measure external threads, you can simply do what I did, machine an external thread at the minus, an external thread at the plus, and now you made yourself a set of go-no-go gauges. So now you can check an internal thread. So there's our practice parts and our camming. So let's wrap it up. I hope you enjoyed this video on thread milling. I know it's a pretty advanced topic and it gets a little muddy in the math. So if you stuck with me through the whole video, thank you and I appreciate it. I'm just trying to do a deeper dive in these videos and really show you the working math and knowledge behind these types of operations that are done on CNC machines. There's a lot of videos out there, you know, they'll show you how to make a thread, but then when you try to go do it yourself, you find that a lot of the steps are missing. So that is complete from A to Z on how to perform thread milling. If you have any questions or comments of anything I didn't cover, or you need some more clarification, please feel free to comment in the video or send us an email. Thanks for watching, and we'll see you in the next video.